Right. Then the next topic is the inverse transform, but at this stage is basically lookup table. The unlike the Fourier transform, we have the transform, the inverse transform, they're symmetric. For Laplace transform, the integral formula for inverse Laplace transform is slightly more complicated. So we'll talk about that in a little bit later. It's not too much, hopefully not too much later. But for now, for many purpose, you can look up table, and the textbook has it as a simple, a very short table of just some basic functions. So this is the function, and the Laplace transform of that function as a table. So you can use that for doing transform or inverse transform. So for doing transform, just look up the function, and then you look up the transform. For inverse transform, you look up compare the inverse transform with what you try to do an inverse transform, and then get the function, right? And if you have if you have a Laplace transform that is more complicated, you probably should look at the larger, more comprehensive math handbook that should have a much longer table, Laplace transform table. Okay, and the only subtlety is that the inverse transform, they are not exactly unique, because you define a Laplace transform for integrals. This is defined as ft, right? It's just integral, so whatever this ft is, or actually start from 0, so whatever the ft, right? And the integral is basically the area, right? And multiply, of course, multiply by, right? But if you deviate from ft by any isolated point, so you just define your uf by any arbitrary point, you define it as a different value. So this value, another location defined as a different value. Basically, your function has this isolated jumping around, and that doesn't affect the area, right? So it means that the area, just given by the area, which is the Laplace transform, will not fix the function, right? And so there could be an arbitrary point that it deviates at this grid isolated way. As long as there are not infinitely many of them, then it doesn't matter. But for physical problem, you assume continuity most of the time. Assume your quantity is smooth, and you don't include all these isolated jumps. Then the inverse transform is like unique. Okay, so then you just when you solve for whatever your problem, you find a Laplace transform. Just look up the table and find the inverse transform. All right, so that's the way we'll do for now until we get the formula, the integral formula, just like the inverse Fourier transform. It's slightly more complicated. And we'll just look up the table and do some examples. All right, so the first example, 20.7.2 is this one is just trivial, just giving you the Laplace transform. And then calculate the inverse transform. But this one is just because it's more complicated than the list on the table. And what you do is just the partial fraction, right? So this is square, and see what you get when s, and then there's a term s squared plus k squared, right? And you want the two add up to be k to be 1 because you pull out the k squared anyway, right? So actually you might not need to pull out the k squared because exactly 1 is a little complicated because you already have a k squared. If you the common denominator s times s squared plus k squared. So it means you multiply s squared plus k squared here, and you multiply s here. So you want to get rid of the s squared, and you have an s here. You get another s, and subtract that. That that should do it. Right? You have s squared plus k squared minus s squared becomes k squared. Right? But this one is it's simple enough to do that. Otherwise, you just write the unknown coefficient and solve for them. Yeah, that is that. And so the inverse transform, what is the notation? Yeah, S, the L inverse, writing it this way. Okay, obvious, obviously. The first one is just 1, right? Remember this? Yeah, this is just 1. This one is a sine or cosine? Look them up. This is S divided by S squared plus K squared. What is that? Oh yeah, the number 8. S divided by S squared plus K squared. So it's cosine of whatever the K, yeah, the cosine KT. Yeah, this one minus this one. Right? This, you know what I'm doing, right? So number 8, you look up the table 20.1, the item number 8. This is this one. Right? Just do it that way. So that's nothing. That's really trivial. Right? Okay, this one. The next one is it be exactly not too much harder. So this integral defined as this integral we know how to calculate that after or the compact integral. In fact, you probably did that before, but this is like using the Laplace transform method to convert that to another integral, which is, I mean, also easy, but it's just an example. Just Laplace transform capital L. That it's just no, it's just applying to the formula. SP and another integral. And then also dt. Right. That is the definition. Now you basically you get reverse the order of integration. Integrate t first. Integrate t first is like just like taking Laplace transform sine tx, which we did that before. Which is if you look up the table, sine number 9, sine kt, except that now is instead of k, we have x. Okay, so you just write down. So we have dx and dx here, right? Taking that, and then the rest is the Laplace transform sine, which is x divided by s squared plus x squared, right? And now you cancel the x, right? And now this one you also know how to integrate that. Either you use this whatever the transform, change a variable. Is it tangent or something like that? Yeah, yeah. You can use a tangent to use it to change a variable, or for us now, you can do a complex integral for this kind of thing very easily because you have just two poles, right? And then the integral is fall fast enough, and the even function, so you extend to the negative to positive and integrate uh, just one residue. Right? Either one plus one residue will give you the answer. But you know the answer. This is um, that is pi over 2s. Right? Um, and that is you also can do a complex integral and get this, and you confirm that that is correct. And, okay, and that is fine. And that is for positive t. That's because we integrate t from all the positive t. For negative t, obviously, this is even this is an odd function in t. So for negative t, you just change it to a negative sign. But zero obviously is a zero. So I think that the next lines of equation is just showing that. All right, so